Okay, so today we're going to do source level debugging of some Embassy code. This is the Hello World application for the H7. So we're looking at the H7 here. So specifically this is for STM32s. So normally to run an Embassy program or to build it, you use the command line. So you would normally go into the directory of the examples for the MCU that you want, so examples STM32H7, and then you would run the build program. And then this would give you some files in the target directory. And we specified release here, so we look in the release directory here. And we see here we've got a blinky and a blinky.bin. The blinky.bin is what you would flash onto the MCU for production. The blinky here is an ELF file, and you can look at the details of the ELF file using the GNU obj dump program. I'm not going to go into that now. So to run the program, you would normally use a combination of cargo and probe RS. So when you run cargo, it runs probe RS. So it erases the section of the MCU that needs erasing, it programs it, and then it runs it. Probe RS also continually talks to the MCU via the debug probe and reads the RTT block in order to provide you DEFMT formatted logs, which is what you can see scrolling up the screen. So, probe RS can also be used to erase the MCU, like so. This will erase the entire chip, so if you had data on there as well, then that would also get erased. And it takes longer than it does to just download just the program that you need. Here you can see it only took 2 seconds, but this is going to take about 23 or 24 seconds. Okay, so the next thing that you can do with probe RS is to just say download. So the cargo did a probe RS run as opposed to a probe RS download. So now we've downloaded the code to it. And if we were to use ST-Link or something like that, we could connect to the MCU and have a look at the flash, and we'd see the program there. So we can do the same kind of thing in the IDE. So if you create a launch configuration, so we give it blinky release, like so, apply. That would then use cargo to build it, right? And it builds it. And you could also create other configurations to run it, like so. So here we're doing run blinky release, so it's cargo, and then we're doing run blinky release, just like we did on command line. And that would run it in your IDE. All well and good, except you don't get the color on the logs. But what if you want to debug it? Sure, you could use like info and trace and debug and set your debug levels appropriately, but no, there's better ways of doing it. So what you can do with probe RS is run a GDB server. So you run a GDB server as follows: probe RS, GDB, reset-halt, protocol SWD, chip, and then whatever the chip is. And it creates an instance of GDB listening on port 1337 on localhost. Right? So then back in your IDE, you should be able to create a launch configuration for remote debug, which uses GDB, uses the same port on the same hostname, which is the same as doing localhost if you omit it, with the same ELF file, and you should be able to press debug and run it. Except there's a problem with GDB. This is the problem. Currently, this is the problem. This is with the version of GDB that's bundled with the latest version of RustRover, which is 15.2. This same problem also exists in older versions of the GNU ARM tools distributed versions of GDB, going back all the way to 14.1. 13.2 is okay, 16 point whatever is broken, and all the very latest version, 17 point whatever, is also broken. So, yes. So I had to fix GDB, and I'll go into some details on that later in this. But for now, let's just switch over to using the one that's got the fixed GDB. So on my Windows 11 machine that we're looking at here, I'm running MSys2, and I built a version of GDB for MSys2 UCRT64. If you use the UCRT64 environment, it means you can run Windows binaries from UCRT64 binaries and vice versa. If you're using things like WSL, Windows Subsystem for Linux and so on, you can't do that. You can't mix and match Windows binaries and non-Windows binaries. And the same goes for MSys2 binaries compiled for a different environment. But if you use the UCRT64, you can. So if you're doing debugging work on Windows, that's the environment you normally want to use. So if you get a fixed version of GDB and do the same thing, you can press debug. It should be running, except that you just don't have any breakpoints. So if I put a breakpoint in here, it stops at a breakpoint. Amazing. And you can step into the code, and because this is async code, it'll probably go to places that you're not really expecting. But this is what it does. So you can see here it's going into the embassy poll function for the timer to see if the timer's ready. And so on. And you can step through all the code. You can step out of the code using the appropriate buttons. And you can see that it's in the RTC driver. You can locate to see where the file is. And you can step into everything, step over everything, and so on. You can also look at the values of variables, like so, just for example. And you can also look at memory. So on an STM32 processor, a memory address that you might frequently see is this one. Oops, not that one, this one. And this is your flash memory, basically. So the first bit is your interrupt vector table, and that's what we're looking at here, which is basically a bunch of addresses. And if you look at this in sort of reverse order, you can see that these are addresses. And if you want to know more about your interrupt vector table, then you can check out the STM32 reference manuals. So you can look at memory. In addition to be able to look at memory, you can look at peripheral memory addresses as well. If you're looking at the reference manual, you can find all the different peripheral addresses. So if you look at the memory architecture and memory organization, you can look at the memory map. So the address that we were looking at there, which goes from high to low on this, we can see that that address we were looking at a minute ago was this address, right? Memory flashbank 1. And if you go further up on here, you'll see that there's all the other various different RAM addresses for quad SPI RAM, flexible memory controller RAM, and so on. In addition to that, you also have all the peripherals. So for instance, we've got all the GPIO registers. So one of the things that we're interested in this particular demo, if we look at the blinky code, it uses PB14 to toggle the LED on or off, right? So if we were to look at the memory addresses for this peripheral, we could find the output data register, this one, which is what's used to control the I/O levels of the pins. And we should see that it's got an address offset of 14. And the initial address is this. So if we look at that address plus 14. Now there's a better way of doing this, but we'll come to that later. So what we see here is this. And if you were to look at the individual bits in the datasheet, you would see that one of them controls PB14's I/O level. And if we were to just run this and then run it again, we would see that this address here is changing when we step through the code. So that's how you can look at peripherals and the memory addresses for the peripherals and step debug through the code and everything. You can also use CLion to do it. And currently the sort of embedded debugging support in RustRover is not as good as it is in CLion. But if you install CLion and install the Rust plugin, you basically get more or less the same thing as RustRover, because that's what we used to do before RustRover was available. So if we kill that and switch into CLion, and you're probably thinking that looks entirely the same. That's because it is pretty much mostly the same. So we're looking at the same code again, same project and everything, and you've got your launch configurations. You can run cargo launch configurations in the same way that we did before. So the run was this one, blinky run, same kind of thing. In here, however, doing remote debugging is different. You go embedded GDB server and you get these options. So I've configured one for using GDB, the fixed version of GDB, because the one in CLion has the same issue. So here we've got a target, the notion of a target, but you basically just leave everything on defaults. We give it the same executable, we give it the fixed version of GDB, we tell it never to upload it. These two don't work because ProbarS's GDB server cannot be used to upload code. ProbarS can, but not its GDB server, so you still have to upload it separately. So the way we do the automatic uploading is by running an external tool before the launch. We give it the same options as before as well. The reset command doesn't work as well, and it should be noted. If it did, it would be better, but it doesn't. I'll come on to that in a minute. And so we say build, and then we say run an external tool. The external tool is configured to just run ProbarS, which lives in your home directory under .cargo bin. And we give it the same arguments as we did on the command line. So we say download, and we say the name of the ELF file that we want to download that lives in the project's directory. And then when we run that, it uses ProbarS download to do it. Now, the reason it says probe not found at the moment is not because the probe doesn't exist, it's because it's still being used over here, probably. Still being used here. There. So we kill that, we go back into CLion, not that one, this one, and then we say go. And it downloads it, and then it runs it. And everything's fine. And this is using the fixed version here. And we can still step through everything, and for all intents and purposes, it's pretty much the same. You know, you can look around through all the things as before. But what's different in CLion is that there is support for SVD files. I don't quite know why IntelliJ haven't ported this feature over. Maybe they run out of time. But anyway, if you configure your IDE to have an SVD file, and you can download the SVD files, and this is where you get the SVD files from. So if you search arm.com for the Keel packs, and search for H7 and devices, you'll find this pack, right? And if you download one of those, you'll end up with a .pack file. Rename it to .zip and then extract it, and then you'll get a directory for the pack, and inside this CMSys SVD directory you'll find an H743 SVD file. Okay, so then you go back into CLion and you configure your SVD setup, which is this, and you can add an SVD file using the source thing. So I've already done that, and then here you get to enable the peripherals that you want to look at and the registers on them that you're interested in. So here we've enabled GPIO-B. Okay, so what this means is we can see the memory. Now, if you get an error here saying it can't read that data, so in order to look at those, there's a command that you need, which is this one. So if you go to the GDB console and you issue show mem inaccessible by default, and it says something else other than this, then that feature is disabled. So then you say set mem accessible default off, I think. Yeah. And then you can say show again. And the other option is on, of course, and so on. So if it says accessible when inaccessible when you look at it, then you won't be able to read the registers. So in that case, you set it to off, confirm that it's set, and then you can see the addresses here after you've stepped through the code once again, or you can restart your debugger. But every time you restart it, you would need to issue this command, unless you create a GDB initialization file, which does it for you every time. You can check the GDB documentation on how to do that. So what it means is that if we go back to our blinky program and press go, we can see that the output data register will toggle between two addresses, two values rather. And if we focus specifically on this bit, when we step through it, we can see that it toggles between 0 and 1. So that's how you can quickly debug programs in CLion and look at the peripherals. Now, bear in mind that the manufacturers that create these SVD files make mistakes in them, and sometimes they omit peripherals entirely, which means that you might need to edit the SVD file and add the peripheral to it. In the past, I've had to do that for the system control peripheral. You can find all the addresses for the peripherals in the reference manual, like we were looking at a moment ago. I think this one existed, but there's also peripherals for the debugger. So the debug infrastructure has got its own peripherals. And I didn't find these ones in the SVD file, so I had to create my own one of these. But you normally have the map, and it's not entirely painless, but it's possible. And you can create your own versions of the peripherals and update your SVD files to look at the peripherals that aren't in the SVD files. So that's how you do that. And this is very useful if you're doing particularly low-level things like looking at interrupts and so on. Or if you just want to know why something is not working. So for instance, if all your GPIO data registers here weren't at their defaults, then that normally indicates that the GPIO peripheral itself hasn't been enabled, or it doesn't have a clock signal going to it, in which case you start looking at the system configuration peripheral to see what clock settings or other flags you may have forgotten. So for instance, this is the clock, RCC, that's the one. This is what I'm trying to find. Yeah, okay. So in RCC, you've got the peripheral enabled registers somewhere around here. Here they are. And you might find that you've accidentally forgotten to enable some peripherals, right? And that would be why your peripheral is not doing what you expect. So here we can see that GPIO B is enabled as we would expect. This also raises an interesting point about how Embassy works, because even though you haven't actually done anything specific in here to enable various peripherals, you will find that peripherals are enabled. And depending on how deep down the rabbit hole of embedded development you're going, you may find that you don't want to enable specific peripherals for reasons of, say, power draw, for example. So you might only want to enable the peripherals when you use them, or only the ones that you actually need to use. So, for instance, if you're going into sleep mode or coming out of sleep mode and you want to make a battery last a long time, you don't want to be enabling all the peripherals if you're not using them. So, yeah, you can take a look at the Embassy early initialization code if you want to dig into all that side of things. But this shows you how you can find out what is enabled by default after you run the init code here. So let's have a quick look now at the GDB problem. So that problem I mentioned earlier about GDB was caused by this bit of GDB code. So when you build a binary file, or rather an ELF file, it contains debugging information. And debugging information needs to be present in order to be able to step through the code that we were stepping through. Even if you build in release mode, you can have debugging information which is separate from the binary, which contains various addresses and offsets and all this kind of thing. So you can still run in release mode and have debugging information available to you. But the problem with GDB, all the versions between 13.2 and the latest version, there's basically null pointer problems with this and this. So when Embassy compiles the Cortex RT crate, when it compiles this, there's an assembly file in this, and when it compiles that, it doesn't put like the names of the directories and so on in the debugging information, which then causes GDB to crash. Furthermore, this is how you can debug the early startup code. With other debugging tools, the process is a little bit more seamless, but with ST-Link and ProbeRS, it's not so great. But say you're running a program like we are now. If you go target help, was it target help? So monitor help, that's the one. It doesn't print anything. You'd be like, why not? That's because that actually appeared in the console here, which is the console for ProbeRS, right? So there's a command here, reset-halt, and that's what we want to do. So you go monitor and then reset and then halt, right? And it'll say target halted. And then if you say step or press this button, it'll show you that exact same arm.s file that we were looking at a moment ago. And that is the assembly that's going to run over. Furthermore, if you right click this and go disassemble, you can see the generated assembly for it, and you can step over each individual instruction when you're in this mode. Like so. And you can also put breakpoints over here. So for instance, this is where it jumps to the main program. Well, the macro part of the main program, but if we set a breakpoint and press go, it'll get there, and then we can say step into, and we can see it doing all the things. if we turn off the assembly output and then do a step again, we'll see that the nearest Rust file that it's got is this one. So it's trying to run the executor. So yeah, so that's how you can debug the early startup code. So that was monitor reset halt. So yeah, so back to the GDB bug. This was the bug in GDB. I've submitted this upstream. I submitted this to the mailing list. So hopefully in later versions of GDB this will be fixed. But it's definitely not fixed in this version of GDB which I'm using, which is this date here. So 18.0.50 doesn't have a fix. Hopefully they'll accept the patch or use them as a basis for other patches and fix it. So your life should be easier. So hopefully that was useful, and hopefully that shows the patch people why this is necessary. Alright, thanks for watching. See ya.